Good. Okay, that's as a warm-up. Are there particular questions about last time? If not, I want to come back to one thing which I think is important, maybe mostly also for practical applications, and that's sort of the theory of how to estimate errors when you make measurements. So think of making a measurement like the police does out here with the speed of the cars, right? That's a measurement which is not infinitely exact, and it depends on how you operate exactly your machine, and on your ability to read off, and maybe on the temperature and fluctuations in the air and so on. So there are errors that come with the measurement. Even if the speed of the car is an extremely precise quantity, you will not measure it so precisely. And if you repeat the measurement many times, then you will have outcomes that are a bit scattered. No? So this would be the speed. Maybe this would be around 50 kilometers per hour. And here there's a scatter, say 45, 55, something. Okay? If you repeat measurements thousands of times, you would maybe see something like this, okay? But you cannot measure 1,000 times, and still you would like to know what is actually the real speed of this car, right? So what you do is you measure n times, maybe 5 times or 10 times, and then you average, and then you take this average as the real speed. But of course, if you measure again 10 times afterwards, and you take the average, then you will get a slightly different number, right? So, but you don't want to measure hundreds of times so as to get a better and better feeling. You want to know after, say, 10 measurements, what is the average that I estimate, and how exact is this average? How exact is this estimate, okay? So, for the first question, say, let's make an example. You take 5 measurements, okay? And so you have 5 values that you measure, like, say, 45, 48, 55, 49, and 53, okay? Then you say, okay, to my estimate of the real value that I would get if I measured infinitely precisely would be, so these are my x, is this random variable, which is the speed here. I just take the average here. And now what we actually did last time is estimating not only the average, but also the distribution of of this probability that we actually don't know. We don't know, all the effects that make this distribution not sharp. No, that can be because of our errors, because of the natural fluctuations that affect the accuracy of the measurement. If you measure a quantum object, then even intrinsically in quantum mechanics you have uncertainty. So that can also be a reason for a scatter of possible measurement values. So last time we said then, if you want to, you would also like to know what is the standard deviation of this distribution, and that you can estimate by actually taking the following thing here. So you take your xi, you subtract this estimated average, you take this square, and you sum over all your measurements, and now you divide by n minus 1. On average, this will give you a good estimate of the standard deviation. Now, what do you do with this? Sorry, this is a square, of course. Well, so this is an estimate of the variance for the variance of this variable. Now, why is that interesting? Because in principle, we want to know how good is our estimate here. In order to know how good the estimate of this quantity is, we should know what is a typical fluctuation of this random variable, no? And this, by the laws that we derived last time, is so this is the variance of a sum of independently drawn variables. So this is the sum of variances of xi over n, and that we said also is the variance of 1 over n squared, sorry, of variance of xi, okay, and variance of xi by definition is the standard deviation of that variable. So this is this width here, and I have n measurements, so I get 1 over n sigma squared. Okay. Now from this calculation you can estimate what the sigma squared is, and then you have a good estimate of the actual error that is associated with this estimate, right? So after having made, now let's put this in practice. After having made these 5 measurements, you will calculate x equals, in this case, just 50. And then you compute this value here, which is so 1 over square root of n of sigma of x. And as I wrote here, okay, so you have to take the square root of this expression, right? So here, if we sum that up, you have 5 squared and 5 squared deviation from 50, and 2 squared and 1 squared and 3 squared. That gives 64 actually. So this is square root of 5 times 4 times square root of 64. These are pretty nice numbers. So this is 8 over 2, 4 over square root of 5, and that is roughly at 1.7 or so, right? Okay. So now you put this together, and then you say your average x, so the average speed, or probably the true speed of the car, will be average plus minus roughly sigma x, which is therefore 50 plus minus 1.7. So this is the scientific way of expressing what you measured. You measure an average, and you estimate also the error that is associated to it. Okay, so this is a basic but very important application of what we discussed yesterday, last time, Wednesday. Okay, I guess you may have seen that yourself already when you did measurements in labs or so. You should always estimate the okay. You should always estimate the errors that you make by measuring a quantity with limited accuracy, right? Okay. So now today what we want to do is that we want to last time I gave you a taste of the central limit theorem, which says the following, that the central limit theorem morally says the following: if you take a sum of a lot of random variables which are independent, okay, not necessarily identically distributed, so each xi could have its own distribution, then under certain rather general assumptions on the properties of these distributions, you will get a Gaussian distribution for this sum. Okay, so this is an extremely general and very powerful theorem that you will encounter many times in your career. So of course you know that the variance of this S is just the sum of the variances, right? So let's call this sigma S squared. So in which sense does this go to a Gaussian? Well, you should actually define a standardized variable. So a standardized variable. So you subtract the expectation value of S, and you divide by the standard deviation, okay, and you call this new variable small s, okay. Then the statement is that when n is large, then this standardized variable will have a Gaussian distribution, namely S has zero mean. It has, of course, standard deviation, which is 1, because you normalized it to have it 1. And the claim is that the probability distribution of S will essentially be Gaussian as n goes to infinity. Okay. But it's sort of important that you think in this rescaled manner, in this standardized way. So if you don't rescale, of course, then the variable becomes bigger and bigger. And of course, this is just the leading behavior. If you are interested in the fine structure on the level of contributions of a single variable, then this is maybe too coarse-grained. But as you look at the normalized variable, which lives on a scale which is normal, that means where the fluctuations are of order 1, then you will see just this Gaussian behavior. Okay. And that you already know from the binomial distribution that it goes to that limit. And today we show that in great generality that this happens essentially always. Okay, last time I gave you a flavor of how to understand that this happens by computing the moments of this large S. No, that was the last thing that we did. Namely, we computed this thing, and we saw that for M even and for M odd, we get something subdominant actually, which is not as important as this here. And for M even, we found something like this times M minus 1 times M minus 3, etc. times 1. Okay. Right. And I claimed that so this you recognize very easily. We assumed actually equally distributed X. Then it's clear that this is just the variance of the whole sum, right? So this is equal to variance of S, or S squared. So the whole thing here is just sigma S to the M. Okay. Now if you look at the standardized variable, where the average was already 0 by assumption of the calculation last time. If you divide by sigma S, then the mth moment will kill this factor, and this will just be this simple product here. Okay? And I claimed last time that this is equal to the moments of a Gaussian, actually. Okay, so this is, of course, x to the m averaged over a normal Gaussian. Okay, or sometimes denoted as n0, 1, a normal Gaussian distribution with mean 0 and variance 1. Okay, so this you can easily compute yourself. You prove that, for example, by induction if you want, but we'll find another proof today via the technique of generating functions that I or characteristic functions that I will show you today. Okay. So once more, what was the logics? The logics was I wanted to give you a pedestrian way of understanding how Gaussians come about. We look at such a big sum. We look at all the moments, so the integer powers of S, and compute them to leading order in n. So there are also sub-leading terms here in n. Terms. That means terms that go like n to the smaller than n to the m halves, and that's also the meaning here. Right. So we found these leading terms of the moments, and we recognize them sort of by guessing that these are actually the moments of a Gaussian. Right. Good. And the way that we calculated that, you will maybe realize later in your career that this is something very good to have in your mind, how to understand how these moments come about. Such things are very often used in field theory and in more advanced topics in physics. Okay, good. So to motivate you more for what we are now doing, I would like to stress once more how important and how somehow general this thing is. You take essentially any random variables, you take a large sum, and you make a very universal statement about what is happening now. So you look at the distribution here, you just standardize it by subtracting the average and normalizing the variance. And the statement is whatever you take, nearly, you get a universal answer. So you're always attracted to the same kind of behavior. That this is sort of a renormalization phenomenon, universality at large scales. When you take large sums of objects, you get something that hardly depends on anything anymore. So this is a very powerful and very beautiful thing that happens here. Okay. Good. So now we embark on something which is more mathematical and maybe quite easy to follow technically. And it's a very powerful tool in general, not only just for the applications that we discussed today, but general characteristic functions or generating functions actually are a very nice mathematical idea. And they are actually the analog of, say, Fourier analysis for probability distributions, as you will see just now. Okay. So I guess you have seen Fourier transforms, right? So, okay, let's start with the definition. So if x is a random variable with a distribution p of x, say, p probability distribution function p of x, then we define the characteristic function, which is a function of the argument t, as the integral over dx px of e to the I tx. So I just take sort of the Fourier transform of this weight function, of the probability weight, right? So this is a Fourier transform if you want. Now from Fourier transform you also know that if I know the Fourier transform, I can recompute the probability function by inverse Fourier transform, right? In general, of course, we are not going into the nitty-gritty of mathematics. That's in general true. Good. So this is when the variable is continuous, or if it is discrete, then you just define it likewise as the discrete Fourier transform, like this times p of x, of course. Okay. Now, if you studied Fourier transforms in other contexts already, then you know what you can do with Fourier transforms and why one goes to Fourier space. For example, if you discuss the free electron model or so, then you know you go to Fourier space, because then derivatives become just multiplications by k, and that makes things much easier. No? You sort of diagonalize derivatives, and that's in some sense also why we do this. Namely, now we come to the explanation why this is called a generating function. The reason is as follows. Take a first derivative of this generating function of the Fourier transform. From Fourier transforms, you know that if you take the derivative of the Fourier transform with respect to its argument, that means, for example, d by dk of f of k, that will be the Fourier transform of f of x times x, right? More or less, up to a factor of I. And let's just see how this comes about. So as physicists, we just bravely derive under the integral. Mathematicians will tell you when this is allowed. That is allowed when the first and the second moment of the probability distribution exists, but we don't care about these details. Okay, so what do you see here? It's just that Ix is coming down. Okay. Now, why is that interesting? If I take that now at t equals 0, then this factor becomes 1, right? And then I just get I times the first moment of the distribution, right? That's the expectation value of x. Okay? So if I know the generating function, I take a derivative at 0 and I get the first moment. What happens if I take the second derivative? Well, it's not very difficult to see, right? Then you get 2 times a factor ix down. So then you just get I squared times the expectation value of x squared, and so on, right? So I'm sure you have seen that with Fourier transforms happening in this way. So this is a very powerful tool, right? So if you are able to compute this generating function, the Fourier transform, then you just take derivatives and you get moments very easily, because taking derivatives is a very easy thing to do. And that is indeed a very, just an elegant way of doing computations in a fast way. And I will show you several examples where you see indeed that this is superbly simplifying your work. Doesn't mean that you couldn't compute these moments in a different way, but this way often is much faster. Okay, so that I will not need. So. Good. So this we can also summarize as a Taylor expansion around 0. t equals 0. No. So the zero order term t to the 0 comes with a prefactor 1. Why is that? Because if I set just t equals 0 here, I get, sorry, the definition was phi x of t is the integral px dx e to the itx. If I set t equals to 0, I get just the integral over the probability distribution, which by normalization is always 1, right? Now I start expanding in t, and so the Taylor series gives me just it x average plus it squared over 2 factorial x squared. So I'm just taking the values of the derivatives that we argued for, namely ix bar, I squared x squared bar, and I form the Taylor series with that, right? Okay. So, good. Well, let's make a simple example, a few simple examples, but which are important. So, the first example is the binomial distribution. Okay. So, for p of x, I take now a binomial distribution. So, or let's call it now not x but k. Okay, and I have n draws. Do you remember what is the formula for that? Yes, n sub k, or maybe like this, times what?
We call p the probability of cycle, then p raised to k.
P, yeah. And 1 minus p to the n minus k, right? Okay, now let's use the definition, that is this, or the discrete version which we need here. So phi of this variable x, which has this distribution, at the argument t is, by definition, right, it is k going from 0 to n of p of k n e to the I t k. Right? That is our definition. I just write k instead of x. Okay? Does somebody see how to do this sum? So let me now write this like this. So this factor is n sub k, but that's a convention to write this. P to the k, 1 minus p to the n minus k times e to the I t k. Does somebody see how one does this sum?
P times e raised to it plus q raised to n.
Yes, very good. Yeah. So you can take this and this factor together. You realize that this is p times e to the it to the power k, right? And then you can sum this binomial expression, and you find p times e to the e to the it plus 1 minus p to the power n. Okay. Now we have the whole characteristic function. Now it would be very simple to calculate the moments. And so, for example, the first moment will just be, well, you know, of course, what should come out, right? So, but let's just do it. So this will be d by dt of phi of x at t equals 0. What happens if I derive here? I get n times this factor to the n minus 1 times I times p, okay? And that should be I times x bar. So I take the I away, and I get just n times p times this factor evaluated at t equals 0, and this factor becomes 1. Okay? So if I do the second moment, what should I get?
N p times 1 minus p.
Not fully. That's one part of the answer.
Minus okay.
Yes. Right? Because the variance, you know that this is the variance, which is x squared. Okay? Let's quickly, well, I'll let you check that. Take the second derivative, put t equals 0, and you get that. Okay? So you see, this is a very fast method if you use it well. Okay? Now, of course, the second moment you knew already, but the third and the fourth moment would also be quite easy to compute. Okay? Voila. Good. So now comes a very interesting example, very important. Yes?
Okay, the first moment and the second moment, they have some physical meaning, but what the physical meaning of those higher order moments?
Okay, I mean, the meaning is the definition, right? But you mean, what do I do if I know them? So well, you know, it characterizes sort of the shape of the distribution, no? These moments. Suppose you have a distribution that looks like this, no? Then you will have a mean somewhere here, and you will have a variance that looks like this. But another distribution will have maybe the same mean and average, right? And then you would like to characterize, but this distribution is much more skewed. It looks like this, no? And this has no skewness, and that is measured by the third moment, for example. Or by
Okay, so the third moment is like whether it is skewed.
yes, if you calculate the third moment with respect to the average, so this tells you something about, this is the first odd moment, which is not 0, because this is, of course, 0, right? So this will tell you about the asymmetry of the distribution, right? So this is often called skewedness or skewness, or actually also kurtosis. So if this is 0, for example, because the distribution is even, if you have something that looks bell-shaped like this, then you know that a Gaussian looks a bit like this, but a Gaussian is very specific, and then sometimes you want to characterize that a probability distribution is almost Gaussian, but not quite. Then you look at the fourth moment and say, how much is it different from that of a Gaussian? Right? Okay. Now, since Gaussians are so important and come up so often, and it's often interesting to have something non-Gaussian because this is exotic, it's important to understand how do Gaussians behave. And Gaussians behave very simply and very, very nicely. Okay? So our next example is therefore Gaussians. A Gaussian distribution. So we take a P of x, which is, let's take the most general Gaussian. So I have this sigma, right? Okay. So this is the standard deviation, and that's the mean of this distribution. Good. And now what do I want? I want the characteristic function, or the generating function, which by definition is the Fourier transform of this thing. times e to the itx. Okay? So who of you does not know what is the Fourier transform of a Gaussian? So you all know? So who tells me what is the result? Yes. Do you know how to prove that actually? How do you prove it?
Formally, you can do it, but
And less formally?
informally, okay. Okay. It is symmetric. Okay.
What is symmetry? So what do I have to do? Yeah, it's the Fourier transform of this thing, but so how do I compute that if you don't know already what is the result? What should I do? I can either go into the complex plane something, or I can do something more fishy, but which is also correct. I just expand this out. I get a quadratic expression in x. I write it as, make a quadratic completion, right? The integral over the quadratic term gives me, cancels just this prefactor, and what is remaining is, so I write this as something e to the minus x minus something squared, and there will still be something like this, plus something which remains. Then I do the integral, this kills everything here, and what remains is e to the a, right? Okay, if you do that here, we don't do that because you all know it, you say, you get the following, e to the itx bar, and then the most important term is this here. So notice that in the Fourier transform, the variance goes from downstairs to upstairs. Probably know that, but if you forgot about this, how can you remember that? You see that t is t times x must be a number without units, no? So if x is a length, then t should be an inverse length. So if x is a length, then sigma is also a length. Now here you have an inverse length squared, and to make this dimensionless, the sigma must stand here. Okay? So, of course, for a mathematician, there's nothing like units in this sense, but for a physicist, this helps you not to make errors. Okay. So, you see the characteristic function of a Gaussian is extremely simple, right? And now it is very simple again to compute moments of a Gaussian. Again, by the same trick, namely that we take derivatives of this characteristic function. So let me see. Yeah, so let's now specify to a Gaussian variable which has mean 0, otherwise it's very cumbersome. And let's compute the moments. Okay. And let's confirm this formula that I gave you last time and in the beginning of this lecture. Okay, so first thing that you should immediately be able to show me is that the odd moments are 0. Can somebody argue that? Mm-hmm.
Okay, this one is x raised to 20 plus 1, which is odd. Okay, we have minus contribution from the left,
Mm-hmm.
and plus from the right, and then we get even.
Yeah, very good. Okay, so is that clear to everybody? We have a distribution which is symmetric. This is the p of x, Gaussian. If I calculate an odd moment, say the third moment, for example, then x to the third looks like this. If I integrate the product, then I get 0 by symmetry, no? By the way, that's a general rule in physics. If you get 0 from a result which is not trivial, there is always a symmetry or there's always a reason. And as long as you don't understand the reason, you haven't understood something important about the problem. That's a very simple sounding statement, but it's a very strong guideline for you to find out in which direction to search. You know, to push your research, you look for some things that are astonishing and that you don't understand. Well, here we did understand, but there are many cases in physics where you get 0 and you don't know why, and that's always the exciting moment because you know there's something to discover. Okay, that's a side remark just on philosophy. It's an important one. So now, what about even moments? So from our general philosophy, we know that this 2nth moment should be just 1 over I to the 2n, and then the 2n's derivative of the characteristic function. And the characteristic function when x bar is 0 is just this Gaussian. So it's this thing here. Okay, so now you have to take multiple derivatives of this thing. And let's do that for a few small n's, no? So for n equals 2, and in the end you have to set t equals 0, right? So if you do it for 2, then you have twice the derivative, and in the end you have to put t equals 0. So if you take the first derivative, then you get down minus t times sigma squared. But then if you set t equals 0, in the end you have to kill this t in front to get something finite. So the second derivative has to act on the t in front and not on the exponent, right? Then you get minus 1 times sigma squared, which came down, and you have a minus 1 from here, so you get just 1 times sigma squared. Okay. Fourth moment, what happens? Each time that the t derivative acts on the exponent, I get down a factor minus t times sigma squared. Okay? But every factor of t that I produce in front, I have to kill again, otherwise it makes me 0 in the end, no? So for each derivative acting here, I need a derivative acting in front. So I have to pair the derivative on the exponent with the derivative in front. So I can use 2 of the derivatives to act on the exponent and 2 to act in front. And what I get out of that is twice a factor of sigma squared, because I derive twice in the exponent. And then I get essentially factors of 1 from killing the t's that I also get. The minus signs are killed with this I. And then I get the combinatorial factor here, which is the number of combinations that I can take to pair derivatives that act on the exponent and derivatives that act on the prefactor. Right? So if you ask, and this is the number of pairings of 4 objects into pairs, and that's 3. For 6, you get 3 factors of sigma squared times the number of pairings of 6 objects. So for the first object, you have 5 possible partners. For the next object, you have 3 partners left. And then for the last, you have just 1. And so that's the formula that I claimed to you, now derived via generating functions. Okay, you see this is a very powerful and simple method to compute moments. Okay, so good. Now, before we go on with further examples and develop the theory of characteristic functions, let me note a few elementary properties of these generating functions or characteristic functions. Okay, so first thing is x is always our random variable. Now if I want the characteristic function of the random variable times a factor a constant a, then it's by definition this is just the expectation value of e to the I axt instead of xt, right? Averaged, meaning integral of over px dx of this thing, right? Now write it just like this. So this is dx px e to the, right? Okay? And this is, of course, nothing else than the characteristic function of x at the argument a times t, right? It's very simple. Much more important, but still actually simple to prove, property is the following. If I take a sum of independent variables, and I want the characteristic function of this new random variable, which is the sum, at argument t, so by definition, again, this is the average of xi times it, averaged over all the probability distributions of these xi's. Now, since they are independent, so I can write this exponential, of course, also as a product of independent exponentials, right? And it's the average. Now, since the variables are independent, the average of the product is the product of the averages, right? That we said again last time. Okay, and that is by definition again just a characteristic function of the variable xi at argument t. So we see that there's this nice property that the characteristic function of a sum of independent variables is just a product of the characteristic functions. If you know Fourier transforms well, then this is nothing else than the convolution theorem. Do you know the convolution theorem? Does somebody know? No? Well, then it's also not worth going into that. Okay. Good. And now let's combine these two things together to get the characteristic function of an average, which I define as always now in these lectures. So let me take the sum of n variables, divide by n, and that's my new variable. And I want the characteristic function of that. So what is that? That is the characteristic function of a certain sum, namely the sum of xi divided by n. Okay, that we know is the product of the characteristic functions of xi over n, and that by the first one is equal to the product of xi characteristic function of xi at the argument t over n. Okay. Now, if I say further that the probability of xi is equal to the probability of xj, so if they are identically distributed but independent from each other, then there is even further simplification. Then the characteristic function, of course there's a t here, will just be the nth power of this, because each variable has the same distribution, right? Okay. So you see, this is a very nice property, very not obvious. If I take the characteristic function of the average, it's just the nth power of this property of the single variable, right? So if we know the characteristic function, if we know the Fourier transform of one variable, we immediately know the Fourier transform of the sum of n variables, no? And then if we Fourier transform back that, we have the probability distribution of the sum, right? And that will give us the theoretical machinery to prove the central limit theorem, because eventually we want to have the probability distribution of this sum, right? And want to show that this always becomes a Gaussian. Do you see where we are going? Okay. So a first easy but very important application of this is application to a sum of Gaussian variables. So that is, I take xi to be a Gaussian with xi equals, let's call that xi I, that's the average, and then, or the mean, and variance equal to sigma I squared. Okay. So we just derived before that phi of xi of t is e to the I t xi I, that's the average, minus sigma I squared t squared over 2. That was the characteristic function of a generic Gaussian. Now let's take this here. So if I define, no, I don't want the average, just the sum. So I want the characteristic function of the sum of such Gaussian variables from 1 to n, okay, of t. And this law here just tells me that this is the product of these characteristic functions, right? Okay, and that's a very simple thing, because these are simple exponentials. So I get here it times the sum of the means minus sum over I sigma I squared t squared over 2. Do you see what beautiful thing this is implying? Can you translate that into words, what we are seeing here? So what can I now say about the distribution of the sum of xi's?
N times.
It has this mean, right? Yeah.
And variance sums.
Right. But that I know even if these are not Gaussian. So the mean of, let's call this variable something, y. So that y mean is sum over xi I, and that the variance of y is equal to the sum of the variances. That is always true, completely independent of whether xi I is Gaussian or not. That's just the independence of the variables, right? So, but what is more particular here?
As if it is the same thing.
yes, it's still a Gaussian, right? This is still a Gaussian. So if I now want the probability distribution of y, what will it be? How do I get the probability distribution of this sum?
Just e raised to the Gaussian. Just replace the mean by y. Inverse transform.
You take the inverse Fourier transform. So how do I do this? What do I have to write? I want the probability. Yes. And then of what? Is that correct? What do you think? Right? 2 pi here, because we didn't have a factor of a square root of 2 pi in the definition. So the inverse transform has 2 pi. So now since you are all proficient with the Gaussian integrals, what do I get if so this is this phi y, no? So now I plug this in here, what will I get? It gives a Gaussian, right? And the only parameters of a Gaussian are its mean and its variance. So I immediately know this will give, but of course you're welcome to check that. Var y and e to the minus y bar squared over 2 var y, where these things are defined by that. So the important conclusion is the sum of independent Gaussian variables is again a Gaussian variable. What about the difference of two Gaussian variables? Yes. Because minus a Gaussian variable is also a Gaussian variable. So a minus b is like a plus minus b. And so this is also Gaussian. Right? So if I take two identically distributed Gaussian variables and I compute their difference, what will be the mean? Identical. So I take A and B Gaussian and they're identical Gaussians. So with equal properties, equal mean, equal standard deviation. So now we just say that C equals A minus B is also Gaussian, right? And with what parameters? As zero mean and the variance.
Zero variance is very easy.
Sorry?
Okay. No, the variance of
The sum of the variances.
Yeah. Okay, let's vote, right? Probe the binomial distribution. I hope it's biased. So what is the variance of C?
Since C is a Gaussian, then the variance of C has to be the variance of A or the variance of B, since both are equal. Then the sum, which is 0.
Ever. This is always positive, right? So what is variance variance of A is equal to variance of B is equal to variance of minus B, right? So this is equal to variance of A plus variance of minus B is equal to 2 times variance of A. Okay, standard deviation, which is the thing that you can much better imagine, that's the width of the distribution, is square root of 2 times that of A. So if you take two Gaussian variables and you subtract them from each other, you get, on average, nothing, but you have a bigger error. Right? Simple thing, but you come across this fact relatively often. So it's maybe good to have it in mind. Okay, so keep that in mind. That's extremely important, and it's actually not so trivial as it may seem, right? Usually it's very difficult to compute the probability distribution of a sum of variables. For Gaussians, you just know what is the answer and how to get the answer by computing this thing. But the derivation is actually not trivial. It's not such a trivial fact. Can I wipe this out? I guess I can, no? So, last important example is the Poissonian distribution. Poissonians. Okay. So, what is P of x for a Poissonian variable x with average, if x average is lambda, x mean? Who won? You. Do you want to say? No. Who would like to volunteer? Yes. Yes. Mm-hmm. Yeah, very good. Okay. It's normalized because if you sum over all x from 0 to infinity, you get here e to the lambda, right? Good. So x goes from 0, 1 to infinity. Good. Okay. So that you already know. Now we want to know what is the probability distribution function of a sum of Poissonian variables. Okay. So now I take n Poissonian variables and I sum them up. That means I have n buckets with radioactive material, and here I have one, and here I have another one, and there I have another one, and now I ask how many decays in total do I have? That would be the sum in a certain interval, right? Now, what do you expect? What will be the probability distribution of this thing?
Roughly? Okay, it is Gaussian roughly, because every, okay, using the same property.
Yes, in principle you're right, but I could also think, well, if these are rare events, the events of 10 buckets will still be rare, no? Shouldn't that also be a Poissonian?
Is it always true? It's always true.
Well, okay, so now we have a puzzle, right? You say Gaussian, I say maybe Poissonian. We are both right.
I'm not precise, just
Yeah.
it's a bigger.
Right, okay, so the answer is we are both right, but there's a catch somehow. So now we need some mathematics to get this right, no? And I actually didn't know that myself, or I never realized it, and then I read it for this class, and I found this an interesting thing. So it's always good to have puzzles, no? Because you think, well, if I think about this way, I should get this answer. Then I think about this way, I get another answer. And then to resolve that advances you in research, no? And that's why we are doing this, because it's fun. So now let's use our technique of characteristic functions to to find out what is happening. Okay, so we need the characteristic function of a Poissonian, which by definition is the discrete Fourier transform of this probability distribution. So I write the probability distribution, and then e to the itx. Okay. So can somebody see how we sum that? Right. Okay. So and what does this give? Okay, let me write it. Okay, x lambda e to the it x over x. Right. An exponential in the exponential. Looks a bit funny, but nothing dramatic, right? Okay, good. So that's the characteristic function of a Poissonian. So what is now the characteristic function of this sum? Essentially yes, but let's take xj average to be lambda j. So it depends on, each bucket has a different number of particles, different decay rate. Okay. So what is then the probability distribution of this sum? So what is now? No, now we use what we derived before. What is the characteristic function of a sum of independent variables? It's the product. Okay, let's do the product immediately. So it's the product of e to minus lambda j plus lambda j e to the it, right? It's equal to e exponential of minus 1 minus e to the it times sum over lambda j. Right? So this is lambda j minus lambda j times 1 minus, right? I have a product of such exponentials. That's the exponential of the sum. Okay? Now, what does this tell me? Yeah. This is a Poissonian again, because this thing, let's call this big lambda. This has exactly the same form as this, no? Just lambda, small lambda is replaced by big lambda, no? So this is equal to the characteristic function of a Poissonian with a parameter with average mean. Let's call this again y. And then y is equal to big lambda, no? Okay, so we have another important theorem. The sum of Poissonians, of independent Poissonian variables, okay, mathematically proved, no question, no? So what's now wrong? Before I told you if I take the sum of many variables, this tends to a Gaussian. And now I show you if I take the sum of many Poissonian variables, which is even more restrictive, I don't get the Gaussian, I get the Poissonian. So something is wrong, no? So what is wrong is that I didn't tell you exactly the fine print of the central limit theorem. No, there are some conditions under which the central limit theorem holds, and we have to be careful about satisfying those conditions. Okay. So grosso modo, what is happening is that if you take a large sum here, and you have, say, identically distributed Poissonians, then this lambda will become large. It will become of order n. Okay, or it will actually be just equal to lambda n if you have identical distributions. No. And then what you see is that this Poisson parameter is not at all small anymore. No, it becomes large. And then the Poissonian becomes bad if is a bad description if the parameter is large, and it actually looks really like a Gaussian when this parameter is large. So you can just plot for yourself how this thing looks when lambda is large, and it looks like a Gaussian. That's very natural, because if you think, how did you derive the Poissonian? You took the binomial distribution, and you just took the p to be very small. But if you take the p large again, you know that you should get the Gaussian. No, there's no sharp line that says here it's Poissonian, here it's Gaussian. This is sort of a crossover. And if you make this parameter, which was assumed to be very small, if you make it large again, you get the Gaussian back. Okay. But you get the Gaussian back only when you rescale your variable. You see that this variable y will have also an average which is large. So then you have to go to the standardized variable. You have to take the average off here. You have to take to divide by the variance, which is also n lambda. And then the standardized variable will look Gaussian. In the tails, it will not look Gaussian. It will still somehow retain the sort of a sum of Poissonians. But then in the bulk, it will look like a Gaussian. Okay, good. Now, I have to go back to... Okay, we are not doing bad. So now we are almost there. So before I now show you how one proves the central limit theorem and that it's very general, let me show you something else which is very important for statistical physics and another nice notion. So we have already seen that characteristic function of a sum of independent variables is the product of the characteristic functions. Okay. Now let's take logarithms. Right. If I take the logarithm of phi and I call this psi, this has a name, and this is called the cumulative function. Okay, these are both functions of t. Now, by definition, it's maybe, just recall you what was the definition. So there's an x here, maybe. Yeah. So if I exponentiate this, I just get this back. Right? And by definition, this was just e to the I xt averaged, right? So what is the cumulative function? Is nothing else than if I insist on writing this thing as an exponential, then the cumulative function is what is this exponential. Okay, can say this is just a definition. But this definition is extremely useful because such averages occur all the time in statistical physics. When, if you have seen partition functions or so, perhaps, and you manipulate them and you try to approximate them and so on, you have to compute averages like this all the time. And it's a very good thing to know how to do such averages efficiently. Okay, and so this cumulative function has a lot of applications. Good. But our motivation just comes from this relation because this cumulative function has a very nice property, namely the cumulative function of a sum of variables is just the sum now of the cumulative functions. Okay, so it's just additive. If I add independent variables, then their sum has a cumulative function, which is just the sum of the independent variables, and that allows to make many computations very, very, very efficiently. Now here we can also expand that into a power series. This function, right? And the power series you can obtain from the power series of phi of x just by comparing coefficients. That's very simple. And you will find that this goes like, the first term is 0 because of normalization. So you have just the Taylor series here. And what one usually does is one defines the so-called cumulants as the coefficients, properly defined coefficients of this power series. Okay. So that's just to introduce some definitions. So these are called the cumulants. Cumulants of x. So this is just a definition. If I take the average of e to the of an exponential of x times something, and I make a power series in this something, then the coefficients of this power series are called the cumulants. And they're important because they have this nice property that cumulants of independent variables just add up when you add the variables. Okay. And I'll just give you, so you can now compute these cumulants or this power series expansion just from the power series expansion of that of this generating function, which you remember had as coefficients just the moments of the distribution. So this has as coefficients the moments. This thing has as coefficients what we call cumulants, and there is of course a one-to-one relation between cumulants and moments. And I just give you the first few relations. So the first cumulant is just the first moment, but then for the second moment you have the relation that it's the second cumulant plus the first cumulant squared, or that is equivalent to saying that the second cumulant is the second moment minus the first moment squared. So this is the variance actually. So the second cumulant is the variance, full stop. That's a very good thing to remember. So if you have a problem where this where you have to average an exponential like that with a factor it here, but in general factor alpha, if this factor is small and you make an expansion in alpha, then you may want to stop at the second order already. Then it's very good to know that what you have to write here is the first moment of x, and here you write the variance, which is also called the connected second moment, or the cumulant. and then these are in lower order of t. So it's very good to know this formula. This simplifies your life a whole lot later. So the third moment satisfies something like this. This is something I hardly can retain by heart, but sometimes you need it. Plus 2x cubed. Okay. So that's, and you can go on, you just compare coefficients of power series and you get this, the connection between cumulants and moments. Okay, I never went beyond third cumulant, I think, or very rarely, but it's easy to do it in case you ever need it. So, now, one important remark about cumulants and Gaussians is, well, you tell me immediately, what are the cumulants of a Gaussian distribution? So I take a Gaussian X, okay, and now I ask, what is e to the psi x of t, which by definition there is the characteristic function. Now you know what that is, right? We wrote it down already twice, now a third time. It's just this exponential, right? Now let's go back to the definition of what cumulants are. The cumulants are just the coefficients of the power series expansion in the exponent. And what you see here is that here is the first cumulant, here is the second cumulant. I mean, without the I, right, by definition. And all the other cumulants are 0. Okay, and that's the special and important property of a Gaussian. It has only two cumulants, and all the other cumulants are 0. So in particular, well, it's also something easy to remember, which is equivalent to what we said before. If you have an exponential of some alpha x, and x is a Gaussian variable, and you have to compute that, well, what do? You just know, okay, this will be, since this is a Gaussian variable, I know this will be alpha x average plus alpha squared over 2x squared minus x, and then plus 0. So this is exact. Because what do I have to do? I have to calculate the average here. That gives me the first term. I calculate the second moment. That gives the second term. And then and then I know that the higher cumulants will be 0. So all powers, all the coefficients of alpha to the 3, 4, and so on are just 0. Because of this nice property. So if x is Gaussian, right? So if you retain that in your memory, whenever you have a Gaussian average over an exponential, you just can write this down without even thinking. That speeds up your work by an extreme amount. If you have to rethink that every time, you spend a lot of time on nothing. So you will see that when you study statistical mechanics in more detail, that is extremely useful if you have this in mind. Good. Yeah.
Do we have only have a distribution with all the cumulants are equal?
All cumulants equal?
Yeah.
Well, you can maybe answer that yourself. I don't know what is the interest of that, but well, it would mean that you have the character. That would mean that your characteristic function is, I mean, by definition, that would be e to the I xt average would be exponential of sum over k from 1 to infinity, and you want them all to be equal to kappa, say, and then I put what? I t k over k factorial, no? Okay, then you can sum that up. You get an exponential here. Then you can inverse Fourier transform. That would be your probability distribution now. But other than a mathematical game, there's nothing in this. Okay. So now we are ready for the central limit theorem. Okay. So what we now want to do is that we want to, we have now the final step, proof of the central limit theorem. And by proof I mean I give you the physicist's intuition of why this is correct, and if you want to know the mathematical details, you can go to any textbook, but we will not have more insight from that. Okay, so we want to study the following objects now. So we take a sum of n variables xi, we subtract the average, and we normalize that by the standard deviation, which is, no, let me not call that Sn, let me call that Yn, and let me call the standard deviation Sn. Okay, Sn is, by definition, the square root of the sum of the variances. Sigma I is equal to the variance of xi. Okay? So that's the thing that I told you in the beginning. You standardize your variable, your sum. So you take the sum, you subtract the average, you normalize by the fluctuation of that variable. That's the standard deviation of this sum. So this thing has 0 mean, and it has a variance which is 1 by construction. No? So why do we do that? Because if I now take a p of yn, the distribution of yn. So when n is 1, then I will just find the distribution of x1. No? So that may be anything. No? So mountain. But it is, I will see it normalized in such a fashion as the mean is at 0 and the variance, so this typical width here is 1. Okay? Then I go to 2 and I see something else, another potato, but the potato is still centered at 0 and has width 1. Now the question is, if n goes to infinity, do these shapes do something universal? And the central limit theorem tells me, yes, these shapes become Gaussian. Okay, so this was 1, and this was 2, and this will be n going to infinity. Okay, and that's what we want to understand now. And the fact that we can ask this question about the shape is because we standardized it. No? So we don't compare apples and pears, apples and oranges, but we compare something which has the same mean and the same variance. then it makes sense to ask, is there a convergence somehow? No? Okay. So in order, mathematically, what we actually need is that we will look at the generating function phi n of t. So that's the generating function of yn. So this is e to the I yn t averaged over the randomness. Okay. And what we will use is a theorem of measure theory of integrability, integral theory is that if this characteristic function tends to a limiting function as n goes to infinity on any finite interval uniformly, I don't know whether you want all these details, but on any finite interval, let's do it anyway. Then the probability distribution, which I call now Pn, say Pn of y, will tend to a limiting distribution as well. So basically, this just says if Fourier transforms converge to something, then also their inverse Fourier transform converges. So that, and this is one of these central theorems in integral theory. That's very natural, right? Okay, and that will be characteristic function. It will be this phi infinity will be the characteristic function of that probability distribution. So the characteristic function of P infinity is this phi infinity. Okay. Good. So this is a little bit of mathematics, which for a physicist is just obvious. For mathematicians, it needs to be proved. Okay. Now, I give you just a slightly simplified version of the central limit theorem, which is perfectly enough for us. And in textbooks, you maybe also find it as Lyapunov's theorem. Okay. Now let's state it correctly. So the distribution of yn tends to a normal distribution. That means a standardized Gaussian, normal Gaussian distribution. I mean, normal means already Gaussian, so it's a pleonasm. If, okay, the xi are independent, normal Gaussian, say, as n goes to infinity, of course, right? So the xi are independent, and secondly, let's make the assumption that there are two numbers such that the second moment, the absolute second moment, is bounded from below and from above, and also the third moment is bounded. Okay. So this I need in order to exclude some pathologies, namely, imagine that I take a sum of xi's where after the 10th value I just add zeros, always zeros, no? Perfect zeros without fluctuation. That would violate this thing, no? Then the second moment of a zero is just zero. If I violate that, then since I add just zeros, I will not tend better to a Gaussian because I just don't do anything. And then, of course, the theorem is not supposed to be valid, right? And you see that this is because I violate this condition. So I need to prevent such pathologies. I should really add something, not nothing. And that's why I need this lower bound. Particularly, we need the lower bound. The upper bound is in order to have distributions that have no long tails, which are also can give you deviations from a Gaussian behavior. Because if you have long tails, then it can be that a certain term in the sum is extremely large, and then that term will dominate everything, and that gives you deviations from Gaussians. Okay, that's why we need these two bounds. This we need to add something substantial and not add nothing, and this in order to prevent rare events. Same here. Okay. Okay, now proof. Proof is very simple, but it will maybe feel good having seen it. So let's define the variable xi, which is the xi minus its average. Okay, so then xi average is 0, xi squared average is the variance of xi, and xi cubed by assumption exists and is finite. Okay, from that follows. Okay, so now let's look at the characteristic function of this variable yn that I wrote down. So, so remember that yn was the standardized sum. So the standardized sum in terms of xi is just from 1 to n xi divided by what I call sigma n. Okay, and sigma n is the sum of xi squared square root. Okay, so the characteristic function now of this object here is, by definition, is the expectation value of exponent it times the sum divided by the sigma n, right? Okay, now we proved or used already many times that this is the characteristic function of psi I at the value t over sigma n. Yeah, okay. Good so far? So now what is the next step? Now what we use is that sigma n is expected, so sigma n is this thing here, and due to my assumption here, this is nothing else than psi I squared, this is at least n times m2, right? So this becomes very large, right? So here it stands in the denominator, so the argument becomes very small, and therefore, when something is very small, a physicist just expands, right? So you expand in this argument. So what is phi psi I of 0? I will first write what is this term? Characteristic function at 0. Monopole. Yes, well, or zero pole maybe. So what is it? It's 1 because it is actually your zero pole, no? It's this. That's the average of 1 is 1, no? So this is the monopole that you would like. So this is psi I to the 1 average, which is what? 0. Right? Okay, so this is 1, 0. What is this? NM2. Well, here is a psi I, so I just have one psi I, so this is the second moment of psi I. Times 2, I guess, right? Let me see. Right. No, it's just this, okay? Yeah, that's correct. Right. That's what we did in the very beginning. The second derivative of the characteristic function is the second moment. Essentially, with a minus sign, actually. And then I write this. So why am I allowed to write that? Well, let's see. So we argued that sigma n squared is of the order of n, at least. It's also smaller than n2, right? So from this it follows that sigma n is of the order of, you can write like this, is of the order of n to 1/2. So here we get something which is of the order of 1 over n, no? And this will be of the order of 1 over n 3/2, etc. And I will show you that we only need this term. Okay? Good. So now we have expanded. Now we put it back in here. So we go down here and write this out as 1 minus t squared over 2 sigma n squared times psi I squared average, right? Plus order 1 over n 3/2. Okay? And this is a product from 1 to n. Okay. Now you can you could go to the characteristic function, or you write this as an exponential. Whatever you do, it's all a bit equivalent. So I now claim this is the same as writing minus t squared over 2 sigma n squared psi I squared average plus order n to minus 3/2. Okay? Because this is already very small, now this is of order 1 over n, I can write 1 minus something small as exponential of minus this small thing plus the same order of corrections, right? And now let's do this product, right? So the product is exponential of a sum. Now I go over here. Okay, so I go on. So my phi n of t is now going to be exponential of a sum over I of what, t squared over 2 sigma n squared, and you have psi I squared, and then plus O n minus 3/2. Okay? So what happens? First term is the most important. What does the first term give? somebody see that? Like this. No? What is this thing? It's 1 by definition, no? Or by construction, because sum of psi I squared is just 1. Okay, and then comes the correction term, and how big is the correction term? I have n terms of order n to minus 3 halves. That goes like order n times n to the minus 3 halves. So this goes like n to minus 1 half. And that goes to 0 as n goes to infinity, right? So I can neglect these corrections if n is sufficiently large, right? Of course, in reality, we'll have to check what it means, sufficiently large. But as a mathematician, you just say this goes to infinity if I wait long enough and take n big. Okay, and now we are done, right? This is e2 minus t squared over 2, which is just a characteristic function or generating function of a normal Gaussian. Okay, and now I use, so this tends to this limiting function, which is what I previously called this phi infinity of t. So now this is the characteristic function of the normal Gaussian, which is my limiting distribution function of y, right? And now by the previous theorem that I stated, if phi n tends to phi infinity, it means that Pn tends to P infinity, which is just e2 minus y squared over 2 over square root of 2 pi. So Pn of yn tends to P infinity of y, which is Gaussian. Okay, and that is the central limit theorem. Okay. So the distribution of our standard variables tends to the Gaussian distribution if n is large, because then these correction terms disappear. So in technical terms, what we are basically showing is that when you take a large number of terms, then the cumulants, the higher order cumulants, become all small, actually of the order of n2 minus the order of the cumulant. What I want to say is, if I take the cumulant of a sum and I take the nth cumulant, then this will behave like n to the minus n minus 2 over 2, I guess. It's just formalizing a bit. So the cumulant of the distribution of a sum tends to 0 with n in this fashion, and only the cumulant of second order is surviving. So for n larger equals 2, and therefore I get a distribution whose cumulants all disappear except for the second one, and that's a Gaussian. Okay. Okay. So that's the culmination of our excursion on characteristic functions. And what you should really retain from this lesson are a few things, actually. Sums of Gaussian variables are always Gaussian distributed. Physically, that means just you can think, if I have already large sums and then I sum large sums, then I will get an even larger sum. And if I know that large sums are Gaussian, then it's normal that if I sum up Gaussians, they are Gaussian. Sums of Poissonians are Poissonian because if I have a few rare processes, then what comes out of a few rare processes is still rare. But if I have many, many rare processes, then they are not so rare anymore and they become Gaussian again. If I take any independent random processes and I sum them up under very mild conditions that the distributions are not too narrow nor too wide, then I get Gaussian distributions for the sums. And for your future, look at this cumulant technology and think a little bit about that. That's a very beautiful and powerful thing. Okay, that's it for today.